Swayam Prabha. Digital India. Educated India.
We are studying rigid rotor, and at the moment we are trying to set up Schrodinger equation for a rigid rotor. So far we have reached a situation where we have written the Hamiltonian. Well, we have arrived at the same Hamiltonian in two different ways. Right. The last discussion we had in the previous module was that we started with the L square operator. We realized that the Hamiltonian is bound to be this L square operator divided by 2I. Hence we got minus h cross square by 2 mu r 0 square multiplying 1 by sin theta del del theta operating on sin theta del del theta plus 1 by sin square theta multiplying del 2 del phi 2. And now we will define the wave function in a particular fashion, and then we will try and separate the equation into individual equations in theta and phi. To do that, first thing we do is we write the wave function as a product of a theta dependent part and a phi dependent part. Let me just paraphrase this expression to you, because generally for us Greek letters are intimidating. There is nothing to be intimidated here. On the left hand side, instead of psi, I have written y. Now yj, what is j, what is m? Let us wait a little bit. I will tell you what they are. They are basically quantum numbers. They are functions of theta and phi that we have written as a product of capital theta, which is a function of theta. So capital Greek letter here is a wave function. Small Greek letter is the variable or coordinate. So capital theta is essentially the theta dependent part of the wave function, and capital phi is the small phi coordinate dependent part. Okay. Why do we write it like this? Because we cannot write it as capital theta plus capital phi, can we? I mean, that would be dimensionally inconsistent. We can multiply, right. So for separation of variables in situations like this, it makes perfect sense if we take the wave function to be the product of wave functions in independent coordinates. Okay. That is a very standard technique of separation of variables, right. Now what I need to do is, I know the Hamiltonian already. I want to take the Hamiltonian and make it operate on the wave function. And here, since I am going to separate the equation into two different equations, we have, as discussed already, written everything in theta in blue except the sin theta, and everything in phi in green. So our purpose will be to get all the blues on one side, all the greens on one side, all theta dependent terms on one side, all phi dependent terms on the other side. That is what we will try to do. Okay. So first of all, look at this, well, look at the second term, that is easier. 1 by sin square theta del 2 del phi 2 operating on capital theta capital phi. Capital theta is a function of theta and not phi. So as far as phi is concerned, it is going to be constant, and capital phi is a function of small phi, not a function of theta. So what is, forget about this 1 by sin square theta for the moment, what is del 2 del phi 2 of capital theta capital phi? Capital theta is constant, goes out, and you are left with del 2 phi del phi 2. In fact, it makes perfect sense to write d 2 phi d phi 2, right, because there is no theta anymore. Capital phi is exclusively a function of small phi, So, there is no point of writing delta anymore. I have continued with delta in the subsequent discussion, but I hope you understand that delta is not even required, d is fine. So, the second term will be capital theta by sin square theta multiplied by d2 d phi 2 d2 phi d2 capital phi d small phi 2. What about this one? Here capital phi will be constant. So, we will get capital phi by sin theta multiplied by del theta operating on sin theta del capital theta del small theta. Okay. So, this is what I get, right. What are we trying to do? We are trying to separate the equation. So, first of all let us multiply by 2 mu r0 square divided by h cross square, that is very simply to get rid of the coefficient here, and we will also multiply it by 1 by capital theta capital phi. Why? Because once we do that, here we have capital phi in the numerator. If you multiply it by 1 by capital phi capital theta, then phi and phi cancel, you are left with capital theta. So, you will get capital theta multiplied by 1 by sin theta, well 1 by capital theta multiplied by sin theta, then del theta operating on sin theta d theta d theta, d capital theta d small theta. Okay. So, in that first term there will be nothing in phi anymore. What about the second term? In the second term we are going to have, well this capital theta will go 1 by capital phi sin square theta d2 capital phi d phi 2. So, sin square theta will be there, but in the next step we will get rid of it. So, this is what we get, 1 by capital theta sin theta del theta sin theta del theta del theta. Remember this del is not even required, d is fine, plus 1 by capital phi sin square theta d2 capital phi d phi 2 equal to 2 mu r0 square by h cross E. Okay. So, I have got rid of the wave function from the right hand side, but even though the first term on the left hand side is sorted, the second is not. So, to get rid of that, it is not very difficult to see what I have to do. I have to multiply by sin square theta, right. But before I do that, let me rewrite this minus 2 mu r0 squared multiplied by E divided by h cross square as minus beta. Why minus beta? Because that is how it is written in solution of Schrodinger equation for hydrogen atom. Whatever treatment we are doing now is exactly the same thing that is done for the angular part of Schrodinger equation for hydrogen atom, right. That is why it is so attractive, other than it describing a rotating molecule in the first place. So, we will write it as minus b. So, what do? We multiply by sin square theta and then we can rearrange, right, because once we multiply by sin square theta, the first term becomes sin theta by capital theta d d theta of sin theta d theta d theta. Second term becomes 1 by capital phi d2 capital phi d phi 2. So, nothing in theta anymore. On the right hand side you have minus b multiplied by sin square theta. You are multiplying throughout by sin square theta, remember. So, if I bring that minus b sin square theta to the left hand side, then left hand side, and if I take this 1 by capital phi d2 capital phi d phi 2 to the right hand side, then the left hand side will be entirely in theta, right hand side will be entirely in phi, something like this. Sin theta by capital theta del theta of sin theta del theta plus beta sin square theta is equal to 1 by capital phi, well minus 1 by capital phi d2 capital phi d phi 2. Please remember the capital letters denote wave functions, small letters denote coordinates, okay. And I have not written capital phi and then small phi in bracket because the notation is such that it is not very difficult to understand. Alright. So, almost done, but now what we see is on the left hand side we have an expression in theta, on the right hand side we have an expression in phi and they are equal to each other. How is that possible? Because variables are different, they can only be that can only be possible if both are equal to a constant, yeah, then it is possible. Then it does not depend on theta, does not depend on phi either. So, we equate this to m square. Now, why m square? Why not m? Why not k? Well, once again the answer is we are not doing it for the first time, somebody else has already done. We know very well that the subsequent treatment becomes not only easy but also meaningful if we write m square here. That is why we write m square and not anything else. Okay. What do we have? We have two equations now. We can write sin theta divided by capital theta dd theta of sin theta dd theta plus beta sin square theta is equal to m square. That is an equation that is entirely in theta, and we can write 1 by capital phi d2 capital phi d phi 2 is equal to minus m square. That is an equation that is entirely in phi and not theta. So, we have achieved the separation of variable that we had set out to do. Okay. Now, we are going to solve the phi part because it is very, very simple. We are not going to solve the theta part because it is very non-trivial, but then the solution was known already when this rigid rotor business came into discussion. So, we will discuss the solutions, they are very important. For now, let us try to see whether it is possible to solve the phi part. Well, it is possible and it is very easy. So, 1 by capital phi d2 d phi 2 is equal to minus m square. This is what we have got. So, let us simplify a little bit. We can write d2 phi d phi 2, and now I have written d instead of del. d2 capital phi d phi 2 is equal to minus m square capital phi. Okay. What is the solution to this? Let us use the trial solution. The trial solution we will use is phi equal to a e to the power plus minus I m phi. Now, one might say that the most general solution is actually a1 e to the power I m phi minus a2 e to the power minus I m phi. Why are we not taking that solution? Why are we taking this? We are taking this because wave functions tell us a story, wave functions has a meaning. That meaning comes out very nicely if we take a part and not the whole, and the part is as valid a solution of the differential equation than what the whole is. So, we will just work with this one at a time. We will work with either plus or minus sign in the exponent. So, this is a trial solution. Please satisfy yourself that if you differentiate it twice, you do get something like minus m square capital phi. You get it? Differentiate once, you get d phi is equal to plus minus I m a e to the power plus minus I m phi. Differentiate once again, you get d2 capital phi d phi 2 is equal to plus minus I m was there multiplied by another plus minus I m a e to the power plus minus I m phi. Okay, that is an eigenvalue equation. The eigenvalue would be the value of whatever this d2 capital phi d phi 2 might be the operator for. Okay. So, this is the equation that we are going to use, going to solve. We know the trial solution already. Now, see, if you remember, phi actually ranges from 0 to 2 pi. Okay. That leads to a very important consequence if you remember Born interpretation. Remember, one of the things that we studied from Born interpretation is that a wave function must always be continuous. What does that mean? Okay. Let us say we start from some point, okay. In the xy plane we go a full circle and come back to the same point. Let us say this point is associated with a coordinate phi, small phi. If we go around, then the coordinate that we reach is phi plus 2 pi, but then it is the same point. Yeah. So, we should single valued, not continuity, I made a mistake, sorry. At the same point the wave function must have the same value. So, from here what we can say is, I do not know why I have written continuous, same single valued is the correct answer. So, capital phi at small phi plus 2 pi essentially is equal to capital phi at phi. Okay. Since this occurs with a period of 2 pi, this is called a periodic boundary condition. See, what we have got here is a boundary condition. Remember particle in a box, we had encountered boundary conditions there. In your harmonic oscillator also we talked about boundary condition. Here the boundary condition arises out of not really continuity, but single valuedness, and it is called periodic boundary condition. The value repeats after periods of 2 pi. Okay. That is what is going to lead to quantization. Let us see. Now, if capital phi at phi plus 2 pi is equal to capital phi at phi, then we can write A multiplied by e to the power plus minus phi plus 2 pi is equal to A multiplied by e to the power plus minus I m phi, right. So, what is the solution? First solution one might think is e to the power plus minus I m phi multiplied by e to the power plus minus I m 2 pi is equal to e to the power plus minus I m phi, e to the power I m phi, e to the power I m phi cancel, you are left with e to the power I m 2 pi is equal to 1, and it is not very difficult to figure out what will be from there. But what we do is we use the trigonometric relationship. We know that the exponential term is really equal to cos 2 pi m plus minus I multiplied by sin 2 pi m, right. So, we write this to be equal to 1. Okay. So, it turns out that cos 2 pi m is equal to 1. So, this is going to be true not only for m equal to 0, but also m equal to plus minus 1, plus minus 2, plus minus 3, plus minus 4, and so on and so forth, right. So, we have obtained this quantum number capital M, which can go from 0 to infinity with increasing with integral increase, integral steps of increase. And now we are curious to know what is the story that this capital phi tells us. What kind of information does capital phi contain? And to say that, we can use something that we know already, okay, something that is rather simple actually. What is that? See, what is phi? Phi is essentially the angular displacement between the x coordinate and the projection of the position operator in the xy plane. So, suppose the projection starts from x axis and starts going round, phi increases, right. So, phi corresponds to circular motion in the xy plane. From our knowledge of classical rotational dynamics, we know that if you have circular motion like this, then the angular momentum is like this. The angular momentum is normal to the plane of circular motion. So, here any change in phi, since it is tantamount to rotational motion in the xy plane, we can expect that the information that will be associated with this wave function capital phi should be the angular momentum in z direction. What is angular momentum in z direction? Nobody has said that the rigid rotor is actually rotating in xy plane, it can rotate in whichever way possible, right. But what we are saying is that when we talk about phi, then we only consider the motion in xy plane part. So, the angular momentum associated with that would be normal to the xy plane, or in other words it will be the angular momentum along z axis. This is called Lz or z component of the angular momentum. So, since phi is associated with circular motion in xy plane, the information it might contain is the information about the z component of angular momentum, right. And we can convince ourselves that that is really the case by starting from the basic definition of angular momentum. We will have to come back to this in the next module as well. So, L is given as r cross p. So, r is written as xi plus yj plus zk. Ijk essentially are the unit vectors along x, y and z axis respectively. P will we have written as pxi plus pxj plus pxi plus pyj plus pzk. Okay. Now, when you take a cross product, then what happens? Something like this. You can write it as a determinant ijk in the first row, xyz as the second row and px, py, pz as the third row. Okay. What is the consequence? You get something like this. I multiplied by ypz minus zpy, j multiplied by xpz minus zpx, well there is a minus sign before that, k multiplied by xpy minus ypx. Remember px, py, pz these are operators, in fact xyz are also operators. So, this quantity ypz minus zpy is essentially called the commutator between ypz, y and no mistake, please delete that, I got carried away there. So, xpy minus ypz, okay, that is not the commutator, it is just two operators operating simultaneously, well one after the other. This is what we get. Now tell me what is the z component of angular momentum from this expression? Along z you have k vector. So, the z component of angular momentum will be xpy minus ypx, that is your Lz. So, how do I construct Lz operator? It will be the same thing, x dot py where without forgetting that these are operators minus y hat dot px hat. This is Lz. Similarly, one can work out that py is equal to h cross by I del del y, px is equal to h cross by I del del x, very simple expressions, you can even remember them, but not required. But you will see we never talk about px and py, hardly ever talk about it. We only talk about L square, the square of angular momentum, and we talk about the z component of angular momentum. Why? Please wait until the next time we meet for the answer. Okay. So, this is Lz. Now, knowing that the operator for py what it is, we can work out this h cross by I x del del y minus y del del x. This is the Lz operator. So, after little bit of hard work we get Lz equal to h cross by I del del phi. Very simple straightforward relationship. H cross by I del del phi, that is Lz, and not surprising because remember what is the operator for linear momentum, it is h cross by I del del x or del del y or del del z depending on whether the motion is along x or y or z axis. Similarly, now motion is along phi axis you can think. So, Lz hat is equal to h cross by I del del phi. Okay. Now, the question that we want to ask is, we had surmised that the phi dependent part of the wave function might contain information about Lz. So, if that is the case, then it should be an eigen function of Lz and it should yield some value of Lz as its eigen value when the Lz operator operates on it. Let us do that. When Lz operates on capital phi, what do you get? You get once again plus minus Im multiplied by A e to the power plus minus Im phi, is not it? Do not forget that there is this H cross by I as well. So, you multiply by that, then you get H cross remains H cross, and this I in the denominator cancels the I that was coming here from the differentiation, M is left. So, you are left with Lz operating on phi is analogous to, well, gives you M H cross multiplied by phi. So, capital M H cross is the eigenvalue for your z component of angular momentum. Okay. M is a quantum number. What is the range of M? Right now we have said from 0 to infinity. Later on we will see that some limit actually does come in. So, mh cross is indeed the z component of angular momentum. What does it mean? What does it mean that z component of angular momentum is quantized? What does it mean by that? What it means is that if you think of this rotation of the rigid rotor, let us say it rotates in this plane, then the plane can have only certain given orientations. Why? Because the arrow can only point in certain directions. Let us take an example. Let us say m is equal to well, let us say half, okay, m equal to half. So, what is the orientation that it will take? Half h cross into well, half h cross, well, half h cross is going to be the eigenvalue, that will be the z component. From there you can work out what the angle will be. So, only certain angles are allowed, and it takes us back to the familiar concept of space quantization that had arisen during Bohr-Sommerfeld theory of hydrogen atom. So, what we see here is that by using quantum mechanics, we see that for a rigid rotor, the angular momentum can only point in certain specific directions, and that means that the plane of rotation can only take up certain specific directions, okay, space quantization. So, this is what we have. Well, next part of the story I will just tell you. We said that the total wave function is theta dependent part minus multiplied by phi dependent part. We have worked out the phi dependent part. One thing that we have not worked out is the normalization constant, that we will do during the assignments. And the solution of the theta dependent part, we are not going to do it. Believe me when I say that the solution is again some kind of a polynomial, but a polynomial in cos theta. It is not x square or y square or z square or even theta. It is something in cos square theta, and we will show you specific values when we talk about hydrogen atom. And again these polymers, these polynomials are actually very special polynomials. They are associated Legendre polynomials, which means that one can write a similar recursion relations among these polynomials as one could for the harmonic oscillator wave functions, right. So, the crux of the matter is that the wave function that is called spherical harmonics is given by a product of a phi dependent part and a theta dependent part. There should be a normalization constant here. The phi dependent part is a to the power plus minus I m phi, and the theta dependent part, it is enough if you remember that it is a polynomial in cos theta. Okay. So, finally, well, here we have put in the constant, and this is what the wave function is. We have the Hamiltonian, we have the wave function. The next step is to apply the Hamiltonian on the wave function, extract energy.